Well, we have reached the very last lesson of the year, 8.5, Making Connections. It turns out that combined functions can be practically used to model a whole bunch of real-world situations. At the very top of your page, you have a picture of a bungee jumper. I don't know if you've ever thought of going bungee jumping, but if we used a graph to think about the bungee jumper and their vertical displacement over time, they're bouncing up and down and they're picking up speed on their way down, and then they're losing speed and then they're gaining speed again. You might think it would look like a sinusoidal function, a wave pattern. But what's happening on every subsequent bounce is that the bumps are getting smaller and smaller and smaller. And so we have a kind of sinusoidal function, but the sinusoidal function is regressing, it's getting smaller, and the difference between the max and the min is getting smaller as we move along, the amplitude, I guess we could say. And so what we actually have is a sort of combined function. We're going to figure out what that function is in different real-world situations. So the first situation we look at is dealing with musical notes. It says musical notes are distinguished by their pitch, which corresponds to the frequency of vibration of a moving part of an instrument, such as a string on the guitar. So there's movement in the string on the guitar, and if the wave looks like this, it's going to sound differently than a note that looks like this, and it's going to sound differently than a note that looks like this. Okay, so that's what we're talking about here. The frequency is how often the pattern repeats itself. The table below lists one octave of the frequencies of commonly used notes in North American music, rounded to the nearest hertz. This is called a chromatic scale. The graph of a pure note can be modeled by the function I, which is the sound intensity with respect to t, which is time, is equal to the sine of 2 pi ft, where f is the frequency of the note, and again, t is time. So according to music theory, notes sound good together when they cause constructive interference at regular intervals of time. Basically what that means is notes that sound good together, if you were to hit them together, their frequency graph would still look symmetrical. It would still look like a healthy pattern. It wouldn't be all like up and down randomly. You'd still be able to see a sequence and a pattern, and that corresponds to how they sound in our minds. So in A, we're going to graph the intensity functions for C and high C. Then we're going to graph the combined function for these two notes struck together, and then talk about the waveform that results. So we're going to use the function given, sub in the frequency that we know for C and for high C. We'll graph those, talk about them a little bit, and then we'll go over to combine those two functions. So here we go. The intensity of C with respect to time is, and I'm just going to copy down the function that we have, sine of 2 pi f, but instead of f here, I'm going to look at the chart, find the frequency for C measured in hertz, which is 262. And that still gets multiplied by t. And then I can simplify this in this bracket. This is the sine of this whole thing, but I have two numerical values here that I can put together. So we're going to do the sine of 524 pi t. Okay, that is the function for C. Now if we go for our function of high C, I'm going to do the exact same thing and take the intensity of high C with respect to time, and I'm going to use the same function. It's the sine of bracket 2 pi, and now I'm going to sub in the frequency for high C, which is 524. And if you're being really observant, you notice that the frequency for high C is twice the frequency of middle C. And I can reduce this, my numerical parts, I can put them together. So we have the sine of 1048 pi t. All right, there we have C and high C. I'm going to get onto Desmos and show what these look like. Okay, I'm here in Desmos and I have typed in our two functions. A couple things I'd like you to notice. I called the first one y1 and the second one y2. All you have to do is type y2 and it will automatically do that for you. Then another thing you'll notice is that this looks really, oh, one more thing. To put in pi, you just type pi and it automatically adds pi to your function. But here you notice you just basically have a blue bar. If I click the red one, I have a red bar, and you think, oh boy, that's not what I wanted at all. But it's just because the frequency is, the period length is so short that this thing repeats itself so quickly that zoomed out this far, it just looks like a big blue bar. So what you have to do is go into settings. I've already changed a couple things in here, but I just wanted to show you what I'm changing here, is that this x-axis, I'm going to just look at it from 0 to 0. Let's say 1. Okay, so that's still too tight, 0.01. Okay, that gives us something to look at, and I've changed the step to 0.001, okay, 1,000th. In order to look at this, again, we're in radians. And close that, put that off to the side, and now we can observe what's happening here. So this is C and high C. So our red guy here is C, and blue is high C. So you can see the frequency of the higher note is, the period length is shorter, frequency is greater, and they both have a standard sine wave. It's not been shifted right or left, and so they both start at 0, 0, and you can see that where C completes one full period, high C has completed 2. Okay, what else can we talk about here? Basically, it just shows that C is compressed by a horizontal factor of 1/2 in order to create high C. Okay, the troughs, that's the low points, and the high points occur at nearly the same points. They both have a max right around here, and then they're both down here when they have a min. High C has a up and down in between there. But you can see how they kind of line up nicely, okay? In order to view the combined function, all I have to do is come over here and hit y1 plus y2. All I have to do to add a combined function is to create a third function, maybe y3, and say that y3 is y1 plus y2. Okay, and now we have this green function. I'll just hide our two original ones. And you can talk about this. This is periodic. It repeats itself. So the max, 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 min, min, min. We have some local max and min happening in here, a little zigzag in between each period length. And it's basically sinusoidal with a slight variation, but it's at regular intervals. So that, just by looking at this, we can say that these notes sound good together, okay? So that's C, high C, and the combined C and high C being struck at the same time. In example 1b, we're asked to graph the individual notes of a C major triad and the combined function. So if we're looking at a C major triad, I've drew a little piano here. We're looking at C, E, and G, okay? So we're going to jot down the frequency function for each of these notes and then graph its combined function, okay? Here we go. We've got the intensity of C, which we've done already. So I'm just going to write that one as sine 524 pi t. We're going to have the intensity of E with respect to time. That's going to be the sine of 2 times, and I look at the function that we have, and then the frequency is 330, so I'm going to double that because we have the 2 times it. So we're going to end up with a reduced function of 660 pi t for E. And then we're going to look at G. The intensity of G with respect to time is equal to the sine of 784 pi t. All right, now all we need to do is graph it using the superposition principle, in which case all I'm going to do is for its combined function, I'm just going to call it y4 because that's what it's going to look like when I'm on Desmos, and all it is y1 plus y2 plus y3, where the intensity function for C is y1, for E is y2, and for G is y3. Let's go ahead and graph that and talk about it a little bit. Okay, we are back in Desmos. I've already got C graphed from the last example that we did. Now I'm going to do E, which is 660 pi t, close bracket. Next, y3, which is G, which is going to be the sine of 784 pi t. And we don't actually need to graph all these, but we'll look at them. And you can see they do peak about the same spot, and then they spread out for a little while. But they do come together again for a minimum and a maximum. And so, I mean, we know this is a C triad, so we know it sounds good together already, but let's go ahead and see what its combined function looks like. We'll call it y4. Say that it equals y1 plus y2 plus y3. If we're hitting all these at the same time, I'm going to make those disappear. Maybe we can even zoom out a little bit. And then we can see it's quite a bit more complicated than the last example that we did, and it's quite a bit more complicated than a simple sine wave, but we do still see there is a regular repeating pattern. Maybe I can change my X scale. Get a few more period lengths in there for us to observe. Okay, there's still a regular pattern. Max, max, you can see it's copying itself almost exactly. There's slight variations within each period. But this suggests that these notes will sound good together. And actually, the variations, we learn that that's actually what gives it its interest. That's what makes it sound appealing to us. It's what makes it grips us. At any rate, that's what the C major triad looks like. In example C, we're asked to graph the combined function between C and F sharp. So I've got my two functions here, and we're just going to quick plug them into Desmos and see what they look like. All right, I've got our two functions graphed here, C and F sharp, and we're noticing that they don't really line up that well at all. The crests and the troughs, the crests being the max and the troughs being the minimums. And so we can assume these notes are not going to sound all that great together. So let's take a look at the combined function. Zoom out a little bit. At first glance, it looks like it repeats itself a bit, but really what we have here is this one is right side up, this one's upside down. The mins are not consistent here. We have like kind of two low bumps, and here we have kind of a mix and match offset bumps. Here we only have one, here we have two. Okay, so, oh, look, this one's kind of awkward. Basically, what we're supposed to be able to see is that it doesn't even appear to be periodic. It's not really repeating itself. It's different kind of every time it goes up and down. And there's very little consistency. And so these are what we would call, if you hit C and F sharp together, it would be discordant. It doesn't sound good together. Okay. So an application of combined functions dealing with music and math. Thanks, Pythagoras. In example 2, we're dealing with the path of a skier. So a skier is skiing downhill. It's a 100-meter hill, and they are traveling at a constant speed of 100 meters per second. That part seems pretty straightforward. If you're going down a hill that's 100 meters long at a constant speed, okay, your graph might look something like that. But they're going through a series of moguls, or small hills. Small hills are kind of bumps along the way. Okay, so you're kind of getting a picture of what this graph might look like. The bumps along the way, if we were looking at this hill kind of flat, they might look like this, right? So basically what we're going to be doing is we're going to be putting our constant downward slope graph, combining it with our mogul graph, and you might assume you could end up with something like this, okay? Which is kind of what you would see if you looked at the hill from the side and you saw those moguls bumping up. Now, we are going to assume that the moguls measure 1.5 meters from crest to trough. So if we look over here, from here to here, 1.5 meters, and that they are 5 meters apart. So from here to here, period length of 5 meters and an amplitude of 0.75. What we're going to do is develop an algebraic and a graphical model of the height of the skier over time. So starting at the top of the hill, and over time they're going to reach the bottom of the hill, and our graph is going to look something like this. Okay? We're going to break this thing into 2 parts. We're going to think about the skier's height, assuming there are no moguls, and then we're going to add the effect of the moguls. Okay? Well, we've already talked about how the effect with no moguls, the skiers, is pretty much just a straight line, okay? And that function is pretty easy to develop. It's going to be height with respect to time equals, and they're going 1 meter per second. So the slope is -1, and this is a straight line with a slope of -1 starting at a height of 100 meters. So we're looking at a slope of -1. So with respect to t, okay, so we've got -1t plus 100. That's this guy right here. Okay, it's not on a graph yet, but you can imagine if I erase this, right, and 100, okay? Which means after 100 seconds, we would reach the ground. We would reach the bottom of the hill. Good. Let's talk about the Mogul situation here. This one's a little more difficult, but we're just going to talk about it using the information that we have and using the sinusoidal information parameters for sinusoidal functions that we've already talked about. So we know the crest to trough distance is 1.5 meters, and our amplitude should be 1/2 of that. Max minus min divided by 2. So we get an amplitude of 0.75. What else do we know? We know that the average speed of the skier, because we need a k value, right? If we're thinking about sine, how would I do this? We're thinking about function moguls, let's call it. Moguls with respect to t is a times the sine of k t minus d plus c. I think that's our standard equation for transformations of a sine wave, okay? So we need a k value here. So in order to get a k value, we need the period length, which is the distance from max to max, from mogul to mogul, which is 5 meters. Okay, so it's 5 meters, and they are traveling at 1 meter per second. Okay, so 5 meters at 1 meter per second. So the frequency is 1/5 of a mogul per second, right? If it takes them 5 seconds to get from here to here, then 1 second, they'll accomplish 1/5 of a period length, okay? That tells us that our frequency, F equals 1/5, or 0.2 moguls per second. We're going to sub those values into the function for frequency that we have. Okay, so this was actually not a super helpful thing to write because we already have a value, a function that we're going to be using. We've got amplitude times the sine of 2 pi frequency times t. Okay, so our k value that I said is kind of like our frequency value in this case. So here we go. We'll plug those guys in. Our moguls with respect to time then, 0.75 times the sine of 2 pi, frequency is 0.2 t. Simplify this, 0.75 times the sine of 2 times 0.2 is 0.4, 0.4 pi t. All right, so now we have the height of the skier with the moguls ignoring the slope, and we have the height of the skier with the slope ignoring the moguls, okay? So we're going to put that together, and we're going to get the height of the skier, their actual path that they're traveling with the slope and the moguls. It's simply going to be adding those things together. So we've got h of t plus m of t. Plug those guys in. H of t is negative t plus 100. M of t is 0.75 times the sine of 0.4 pi t. And now we can get on Desmos and graph that. All right, here's a quick view of our independent functions. Here's our slope without the moguls, and here's our moguls without the slope. And I'm going to put them together. Boom! And you can see what we got here. If we zoom in, there it is. Starting at a height of 100 meters and at a negative slope of 0.1 meters per second, you will get to the bottom of the hill after 100 seconds. Not much to it. Okay, so a variety of real-world situations can be modeled using combined functions. In order to do that, we need to look at each component function, that means each individual function, and then combine them using the superposition principle, basically just putting a plus sign in between them, and then talking about the different key features and analyzing it a little bit. Okay. Your practice problems are noted for you there. They are from page 469, numbers 1 through 12.